Welcome to Diving Dynamics by Alauddin Janae Adam and Renee for Dynamics Fall 2024. Introduction. Diving Dynamics explores the motion and forces involved during a dive, encompassing aspects such as trajectory, stability, and the impact of control inputs on a body and input object as it moves through the air. The aim of this project was to apply the concept to the learning class in the sport of diving to create a simulation of various dives using a simplified human model as shown below. The simplified human model consists of a sphere for the head, a cuboid for the torso, and for the forearm and arms and legs of our cylinders. In this project is divided into three phases. Phase one was the calculation of the center of mass, moment inertia, and basic physics principles for the humanoid in three different configurations. Phase two was modeling simple dives by changing simulating the change of configurations in the air. And phase three used the Euler's equations and simulating 3D dives with a MATLAB ODE45 solver. The center of mass was calculated in phase one portion using MATLAB, where each simple body part's center mass was found relative to the body frame and combined together to get the total center of mass. The center of mass for the open, lance, and pike are shown on the left. And for the open, and these are the three configurations that I was talking about. As you can see, later on in the presentation, you'll see the humanoid change from open to pike to even lance. The moment inertia, to calculate the moment inertia for a 3D guide, we combine the moment inertias for each given component, for each given body part, with the parallel axis being shown over here. And use the standard formulas for shapes such as cylinders and rectangular prisms to get the moment inertia for each body part, for each singular body part. And that's how we got the diagonal terms, as you can see in this bottom right point. For the off-diagonal terms, we had to use the product of inertia for the pike configuration. And for the special case, was the dance carriage, where we had to use an inertia tensor and transforming of the inertia tensor using rotation matrices by negative 30 degrees. The rotation matrix we use is this one right here. We transform it negative 30 degrees at the x-axis to get the off-diagonal terms for the dance configuration. And you can see the legs and arms are turned 30 degrees. Therefore, this rotation, this transformation matrix came out really good. Thank you.
Calculated the initial velocity of the center of mass by setting up generic equations, creating systems of equations, and then solving those systems of equations using MATLAB. First, we created generic kinematic equations from what we know about the system, which is that the diver jumps from the point 0 hcm with unknown initial velocities in the x and y direction, and with an acceleration of negative g in the y direction and 0 in the x direction, which gives us our equation that we see at the top of the screen. After setting up our general equations, we identified some known conditions and used them to create a system of equations. We knew that halfway through its arc, y was equal to 3 meters. We knew that y was hcm after completing its arc, and we knew that y reached 0 at the same time that x reached h. After substituting these conditions into our generic equations of motion, we had 4 unknowns and 4 equations. So we used MATLAB's equation solver to solve the system and generate our complete equations of motion. Finally, we needed to solve for the total time before the diver hit the water. We used the fact that the diver's position was known to be 3 meters minus h plus cm when it hit the water to calculate the total time of the dive, and that completed our analysis. In order to simulate 3D rotation of the diver, we need to study Euler's dynamical equations. Now, these worked really well for us in phase 2 because whenever omega x and omega y are 0, we're able to simplify this equation a lot and solve it analytically with our knowledge of differential equations. However, in phase 3, we begin to have rotations in all 3 directions because we now have a product of inertia, and that complicates this equation a lot and means that we're no longer able to simply solve it analytically. So, in order to solve this equation for phase 3, we need to begin to use more advanced software like ODE solvers in order to find our solutions and simulate the system properly. In order to simulate our code, we chose to use ODE45 as our ODE solver. Our code works by taking in a time vector, moment vector, initial conditions vector, and the moment of inertia at that specific location, takes it into a function and then outputs the derivatives in a way that MATLAB can understand it. So on screen, you can see my ODE45 loop, and then the function that takes in our important variables like the moment of inertia tensor, the time, whether the position is changing or not, the initial conditions, and then solves for the derivatives and gives them back to MATLAB in the way it likes. So one of the important things that our code does is it does this all in a loop, so it's very easy for us to implement. So we have a vector called changing position, which defines whether or not it is the position is changing currently. And depending on that, in our ODE function, it will calculate a moment of inertia derivative tensor, which is very important for the position changes and getting the correct physics during that, which we want to be linear, which is what this function does. So all of that is at work in the ODE45 function, and then it's looped on itself. And so the first time it takes in the initial conditions that we give it initially, and then from then on, it'll loop and take the final conditions from the previous loop as the new initial conditions. So that's kind of the way we've looped the function in on itself. And in order to loop it properly, we have to change the vector of the moment of inertias, the vector of changing position, and the time vector, because we've split all of our times for each position up into different individual vectors within a cell array. So we put all the code into these positions to make it just as easy as possible to get it to loop, and that's what it currently does. So it can be very compact and still generate the results we want. And so after it's looped and everything, we plot it all to make sure everything looks as it should, and then we calculate the total twist and the total flips for our simulation. After finishing our ODE45 simulation, we get back an array called y, which we can then index out to get back all of our important variables that the ODE45 function solve for, like phi, theta, psi, and all the omegas. Then we can plot that all onto separate graphs and see the continuous flows of our different information and how they all change throughout our time span. Finally, we need to make sure that our simulation is actually accurate. One of the best ways to do this is to make sure that it follows conservation of angular momentum. Conservation of angular momentum is something we know will always be true, so if our simulation follows it, we know that we are obeying the natural laws and that everything is going okay. So I have on screen a little function that I created that essentially just goes through each time step and then calculates the angular momentum at that time step, then adds it all into a single vector and plots it at the end. So if this is correct, we should see it be constant at a singular value, or that's what is true in real life. But of course, this is a simulation, so we expect some variation. And as you can see on the graph included beside it, we stay very close to around like 55.54 something. This is all dependent on how tight the tolerances are on your ODE45 simulation. So increasing those tolerances is something I did and is a big way to decrease the variation in your angular momentum to get to a point where it's not varying that much and we can feel pretty confident that our simulation is accurate. Now that we've finished covering how our simulation works, I'm going to try and explain how our animation process works. So first thing, we establish a figure and a structure to contain all of the data necessary to later compile our animation into a full video. So essentially what we'll see is this structure ST. We will input data into it each time we loop, and then we'll combine all of that data into a video. So that's going to be the real key part of our operation here. Next, we start our loop based on the number of instances that we simulated. And then we've got a little setup to start flags each time we change parts of our time vector, because that's when we change positions. So it's important for us to do our later rotation processes to know exactly when we're changing positions. So next, we get on to the largest part of the code base, which is all of our matrices that are actually handling the rotations. So the first three are the most important, and that handles the rotations of everything. Those are pretty easy. It's just basic transformation tensors that are going to rotate things about each axis combined together. After that, it gets a lot more complicated. I'm not going to get too deep into it, but basically you have a ROT, which is a factor of how much things should be rotated at that specific time. And then we have a lot of different rotation matrices for all of the different ways I want to animate the arms and legs of the diver. But that's a lot to get into in such a short time span, so we're going to move past that. But that's essentially the point of all of this. Next, we get into actually calling one of our rotation functions and then giving it the correct information so that we can rotate each body part. So what happens is you input the base rotation matrix, where the center of mass is at each point, and then any additional rotation matrices that need to be inputted. So you see things like the torso and the head have no additional matrices inputted because they're not rotating in strange ways. But you input all of that information in the rotation function, it'll rotate things properly and then transform them to where they need to be at that specific moment to align with the center of mass. Finally, we're actually plotting everything. In previous versions of the animation software for more two-dimensional stuff, we would plot with rectangles, but here we decide to plot everything with patches and to essentially create rectangular prisms at each location to simulate the arms and the head and everything. So we do that, we assign colors to everything, and then we can change the view. So for this, we did two views, one in a more three-dimensional look and one in the classic two-dimensional look, so we could then edit them side by side, which is what we're about to see. And finally, we use the video writer function in MATLAB to combine all of our data in the structures that we sent to the structures using the getFrame function. So we use the getFrame function each time we have our finished graph, put that into the structure, then use the video writer function on the structure to create our finished videos that we will now show.
In conclusion, in this video part, we explored the dynamics of diving through detailed analysis of center of mass and moment inertia across various configurations, calculating initial conditions and their resulting center of mass responses, and simulating 3D rotational dynamics using ODE Solver. By visualizing the results of simulated dynamics across multiple phases, we demonstrated how changes in body orientation and dynamics impact overall motion. This comprehensive approach provided valuable insight into principles governing human diving dynamics, emphasizing the importance of accurate mapping and simulation techniques in understanding complex physical systems. The methodologies and concepts we used in this study, such as the center mass analysis and limit of inertia calculations, and solving rotational dynamics with ODE solver in MATLAB, has direct application in aerospace engineering. These principles are fundamental in simulating and understanding the motion and stability of aircraft, spacecraft, and other aerospace systems, where precision and dynamic modeling is critical for performance and safety. Thank you, and happy holidays.